Welcome to this video on 2's complement. Now, nearly all computers work in pure binary. That means they can only use ones and zeros. So you cannot use a plus or a minus symbol. In that case, how does a computer represent negative numbers? So they have to do that in a different way. Now, we can represent a negative number in binary by making the most significant bit a sign bit. At the minute, we've only been looking, until now, we've only been looking at unsigned binary numbers. When a binary number is a signed number, it has a most significant bit, which will either be positive or negative. So let me just show you that. So if I've got this number here, 1, 0, 1, 1, 1, 1, 0, 1. Now, this one here, that is the least significant bit, the one to the far right. The most significant bit is the one to the left. Now, the bit values are exactly as we would do normally, so let's give them those. 1, double that, double that, 32, 64, 128. Now the difference here is because this is a signed number, okay, it's not unsigned, it's signed. The most significant bit is a key bit. We need to look at that bit, because if it's a 1, the number is negative. If that was a 0, we would know that the number is positive. Here, the most significant bit is negative and the other bits are all positive. So you would start with minus 128, because we know that because this is the most significant bit and it's a signed number, this column here is now a negative number. So how could we work out what this number is? Now there's two methods, and I'm going to show you both methods. Method 1 relies on you being good at maths, which, as you well know, I am not. But if you are, then this method would work perfectly well for you. Normally, on a unsigned number or a signed positive number, you would look at the bit values and you'd bring them down. We now know that this is a negative, so we just bring that down. So it's minus 128 plus 1 lot of 32 plus 1 lot of 16 plus 1 lot of 8, 1 lot of 4, no lots of 2, and 1 lot of 1. If I added minus 128 plus 32 plus 16 plus 8 plus 4 plus 1, that would equal minus 67. There's also a second method for converting 2's complement to denary. You've got a signed binary number, and we know that by looking at the most significant bit. If it is a 1, then we know that the number is a negative number, and to work out what that negative number is, well, to converting it to a denary negative number, we can actually flip the bits. So we've looked at method 1, how we just add all the numbers up, including the most significant bit being a minus number. So if you're good at maths, that's great. But if you're like me and not very good at maths, the flipping the numbers is very, very simple. So let's give ourselves a signed binary number, which the most significant bit is a 1, so we know that this is going to be a negative number. So we've got 1, 1, 1, 1, 0, 1, 1. Now, the trick here is to find the rightmost one. The rightmost one. In this case, it's this one. That rightmost one stays the same, and anything to the right of it stays the same. So the rightmost one is the end one for this one. Now every other bit to the left is flipped. So if it's a 1, becomes a 0, and if it's a 0, becomes a 1. So we flip them. We now use the bit values at the top to work out the number. So I'm just writing those in. So we're looking at this number here, the one that we've just flipped. I've got one lot of 1 plus one lot of 4. That equals 5. However, remember that this is a negative number because the most significant bit here is a 1. So therefore it's minus 5. Let's just have a look at another example. Perhaps doing a more complex, not more complex, but another example using both methods. Let me just flip my page. Here we go. So this gives itself another number, and I'm going to do method 1 first, then method 2. So we've got a number 1 1 1 1 1 1 0 0. There it is there. Now method 1, that's when we apply the bit values to the numbers. We can see that the most significant bit, remember this is a signed binary number, the most significant bit is a 1, so therefore it's negative, so that's minus 128. So minus 128 plus 64 plus 32 plus 16 plus 1 lot of 8 plus 1 lot of 4. We've got 0 lots of 2 and 0 lots of 1, so we don't have to add any of those. Add all of those up, as if by magic, I have the answer here. It's minus 4. That's what I worked out earlier. But if you added those up, minus 120, put minus 128 in your calculator in your head, and then add each of these positive numbers to it, you would end up with minus 4. Let's do exactly the same number using method 2. We've got 1 1 1 1 1 1 0 0. I'm looking for, I know that this is a signed number, I can see that the most significant bit is a 1, therefore this is a negative number. I want to find the denary equivalent, so I'm going to look for the rightmost one. This one is the rightmost one. This one and those to the right of it stay the same. They are not flipped. They stay the same. Everything to the left of the rightmost one gets flipped, including the most significant bit. I then work out the denary equivalent. Well, that's 1, 2 and a 4. I don't need to go any further because the rest are zeros. I've got 1 lot of 4. That's 4. Remember, it's a minus number. Minus 4. So you could use either method to work out or convert a 2's complement to denary. But in the exam you may be asked to provide the decimal or the negative equivalent of a decimal number. So for example, in the exam they could ask you for the negative equivalent, negative 12 for example, to say what is minus 12 in binary. Now what you need to do in this instance is, just as we would flip a positive number in order to get to a negative number, we need to do the same thing here. First of all, we're going to work out what 12 is in binary using 8 bits. So we put our headings down. I know that I'm going to have none of these. They're far too large. I'm going to have 1 8, 1 4. So I know that this number is 12. Okay, but this is positive 12. You can see, because the most significant bit on this signed number is a 0. So what I need to do is I need to flip this number in order to present minus 12 in binary. I look for the rightmost bit. The rightmost bit is this one here. This remains the same, so does everything to the right of it. I then flip the bits to the left. This is minus 12 in binary. And I could then backtrack, I could double check that that's right by doing either method 1 or method 2. I could add minus 128 plus 64 plus 32 plus 16 plus 8 plus 2 to find out the answer. Or up here, you can see that it's going to be minus 12 because 8 plus 4, because this is that flipped, 8 plus 4, it's a minus, it's a, remember it was a minus number, and there's your answer. So it's about flipping the bits in order to work out your, if you've given a denary number to work out the binary, and method 1 or method 2 you can be used to work out from binary to denary. It's not difficult, it just needs to be practiced. There's plenty of examples and numbers for you to practice with on the learning platform. Give them a go and you'll be an expert in no time.